Okay, an example of a transformation similar to the one we just did, but with some specific numbers, is this. Okay?
On y, should that be 2, negative 5, 2?
2 negative, yes, it should be. Thank you. Okay? Okay, well. So the image is the span of the set 1, 3, 2, 2, negative 5, 2. Because, of course, 0, 0, 0 vector doesn't add anything to the span. Okay? Now, in general, whatever your columns are, if this column is set besides 0, 0, then it would be that you'd add that to the span, right? So you typically have 3 vectors in the span, but here you only have 2. Okay? But you can actually visualize this. This is in 3 dimensions. The vector 1, 3, 2, if x is this way, y is this way, and z is this way, is 1 unit this way, 3 units this way, 2 units this way, about here. So you have multiples of this vector. Here, 2 units, negative 5 units, 2 units, a vector about in this direction. These 2 vectors, if they originate at the same point at the origin, form a plane. And any sum of multiples of those 2 vectors is in that plane. Okay? That's an important thing to understand. It's an important thing to visualize. Now, if it was in 4 dimensions, and I had 2 vectors, well, it's kind of like a plane spanned by 2 vectors in 4 dimensions. We have no idea what that looks like because we can't visualize over 3. Okay? We can still kind of see it as it would be in 3 dimensions, okay? Can kind of understand it. Okay, well, that's the image, and the span of this, well, is that, well, those vectors are clearly not parallel. Just from the hand waving I did, it's obvious that this isn't a multiple of this, okay? If it was, then this would have to be twice this, right? Because the 1 and the 2, but this isn't twice this, and this isn't twice this. So it's clearly, but normally, to determine whether these vectors are linearly independent, you'd have to reduce a matrix with those columns, right? Okay? Or with those rows. Reduce the rows. Okay. Make sense? Okay. Okay, I don't want to say too much more about that.